models for cell migration as active gel models. Okay, but now we are still back to some basic physics introduction. So I go slowly again. The idea is that we already discussed sort of one-dimensional elasticity. So the situation we started off at the very beginning was that I was saying, need to do a mechanical test, right? And the relation to the real title or real subject of my contribution is actually that cells do this test, okay? So if you take an adherent cell and put it on a substrate, it will actually start pulling on it with relatively high forces. We clarified all the numbers last time because it's testing the substrate and then it makes decision, for example, does it want to differentiate or not, right? And therefore it makes a mechanical test, and the mechanical test is of course the basis of all of elasticity theory. So what we do is we cut out a piece of material, we pull on it with a force couple, we have an area here and we have a length which is changing. And we clarified in the very beginning that the stress force per area. So it doesn't make sense to think about single forces. We want to think about interfaces which are under distributed forces. And the strain is this delta L divided by L, the relative change in length. Dimensionless quantity, which is very convenient, okay? And then we said, in the end, we also need a material law. And the simplest material law you can think of would be that there's a Young's modulus in linear elasticity theory connecting strain and stress. Okay, so this was our sort of 1D version of elasticity to start with, and now we want to go to 3D, okay? And the one thing which now becomes important is that forces are actually vectors, and also surface because they're normal. And this means we have to introduce indices, okay? And what used to be a scalar stress now becomes a stress tensor. Sigma ij. What used to be a scalar strain now becomes a strain tensor. And what used to be this law here becomes now really complicated, okay? Because on the one hand side, we have the index ij. On the right-hand side, we have now the strain tensor, which has completely different indices, let's say K and L. So there must be a tensor of rank force in between, which looks like this, okay? So you see that immediately you get a lot of freedom in the system. The material properties could be very complicated because you get this huge matrix. And these are just the linear coefficients, okay? Now, in principle, we could also have viscoelasticity, so there could be sort of another matrix for viscous effects, and there could be nonlinear effects, okay? So the number of elastic constants could be potentially huge. Okay, so how do we define these tensors? So this is sort of easy here. In principle, if I look at this derivation again, what now happens is that I have two vectors at the same position. So I have the surface normal, which has a certain direction, and I have the force itself. So maybe I now draw a force like this, okay? So vectors I draw with an underscore. So basically the force could now pull on the surface normal in another direction, okay? And we now define the stress tensor by these two indices, where the second index is the direction of the surface normal. And this here would be the direction of the force. Okay, so I mean, just if I take something arbitrary, x, y, it means I take a surface normal in the y direction. So it's an x z direction, plane. And then I pull with a force in x direction. So this would be a shearing force, right? So to get this situation right, it's actually in engineering very common to draw the so-called free body diagrams. So basically, I do it only in 2 dimensions here, x and y. And then I have obviously four normals, okay? And let's say I'm pulling with a force in that direction. This would be sigma xx, okay? And then I would have another force in the other direction. Of course, this is a function of position, okay? So it would be, of course, like this. So here would be another stress in that direction. It also would be sigma xx, but of course at another position. So it's basically indexed by these variables, if you wish. And importantly, we always define stresses to be positive if they are actually in the direction of the normal. Because the normal has changed its direction and we want a positive number, the force has to be also in the other direction, okay? Yeah, so to continue this, we have these four forces here, but then we also have shearing forces. And here I better look at my notes before I make any mistakes. So let's say we are applying a force in y direction on the surface which has a normal in x direction. This would be, as I explained, sigma yx, because the normal is in x direction, the force is in y direction. Okay, and we give it actually a positive value if it goes in this direction. So if the yeah, so this is always defined to be positive if the two directions go in the two directions go in the same positive direction. Okay, so positive x and positive y, then we call it a positive sigma. Yeah, then you go on. Okay, so here up here would have shearing force xy, the other way around. Down here, if you want to keep this dimension, you have to draw the arrow to the left. And here you also have to draw it to the left. Okay, these are just conventions. And in 3 dimensions would have also the normals in the other direction. So this is the way we now define the stress tensor. There's nothing complicated here except one aspect of it, namely that if you deform an elastic system, you always have two configurations. You have the initial configuration and the deformed configuration, okay? And you have to decide in which of the two you actually measure or define your stress. And that's a very complicated issue in nonlinear elasticity theory because you have to do complicated geometrical transformation between the undeformed and the deformed one. And there's a difference between the Euler and Lagrange frames. I'm not going into this. We don't need nonlinear elasticity here anyway. But this introduces a geometrical nonlinearity in the system. Okay, one of the two nonlinearities you can have in elastic systems. Okay, if you now do the force balance, and you can also do the torque balance. So you look at both rotation translations if you wish. Then you basically have to all these different elements. You do Taylor expansions because they're close to each other. And then you see, of course, that what actually stays will be the derivatives. Okay, same argument like before. If there is a constant force, it doesn't matter because it immediately balances each other. But if there's a gradient in force, this makes a difference. Okay, then things should move somehow and deform. So if you do the force balance, what you get is an equation which just looks like this. You get the divergence of the tensor should be 0. Actually, this is a tensor, and then this should be a vector. So I put these lines here. And if you do the torque balance, you get that the stress tensor should be symmetric, which means it doesn't matter where you do the summation here. By the way, I'm using Einstein convention here to everyone. Okay, so if I write something like this, there is a summation over I. So double occurring indices are summed over. Okay, so this is more or less what's called the Navier equation in elasticity theory. And with this, we get differential equations, okay, like before. Now we can think about the second element here. This is the strain tensor. Yeah, strain tensor, of course, becomes very complicated now because I define it to be delta L by L. But now I'm sitting somewhere in my material and I can look in arbitrary directions, okay? So there are infinitely many strains. On the other hand, it's a well-behaved theory. I know that things are continuous, and I mean, it's easy to understand that in principle, there should be three main axes in which I should look, and this should give me, okay? So in principle, the way it works is that we first define strain in some direction. So strain in direction n. So I'm sitting here, I'm looking in one direction, okay? And I'm asking how much does the material deform in this direction? And then I assume there must be some tensor such that when I contract this tensor with this n, did I call it small e or large e? Yeah, I call it epsilon, of course. I come to this in a second. If I contract the tensor with this one direction, then I should get the strain in that direction, okay? So in this way, I actually define my strain tensor. Now, if you look into the books, you will see that there are many more definitions of strain tensors. It's not the only way you can do, but if you actually go to linear elasticity theory, this becomes the only one, okay? So the strain tensor can be derived to be 1/2 di uj plus dj ui. So it's the symmetrized derivative of the displacement. And it's sort of a unique definition in linear elasticity theory. But there are more choices, or yeah, let's call it variants in nonlinear elasticity theory. Okay, nonlinear elasticity theory. They have strange names. I always forget. Almanzi, strain tensor, and Lagrange strain tensor, whatnot. Okay, and all of them, however, all of them are reasonable. All of them used by engineers for certain purposes, but all actually come down to this one if you do the linear.
The delta L over L equation entirely in Einstein notation?
Yeah. No, here's not Einstein notation because.
Like instead of using.
If I. Yeah, so you just write it like this. You sum over I and you sum over J. Yeah. Okay, my hand. No, it's also because everything is low here. Okay, this is one thing we can actually learn from it right away. So if you take the trace of the strain tensor, so you sum over the diagonal. Here, this is the same like this. So the 1/2 goes away. Okay. So the way I would write it is actually U K K. No, wait. DK UK. And this is nothing else than the volume change in the system. Okay. Why? Because in principle, you take the three main eigendirections of the strain tensor, which is typically orthogonal. In each of them you have a delta L, okay? So it's basically delta Lx times delta xy times delta Lc divided by the else products, and this is delta V divided by V, okay? So the relative volume change you get by contracting the strain tensor. And this is actually also answers a question I got about the active stress or active strain. So if you put in active stress, I mean, one way to actually justify it is that you say you have a chemical potential, and this basically leads to an active stress. You would write active stress is proportional to chemical potential, and you have some kind of activity coefficient in front, okay? Like also Euler showed us this morning. But another way to look at this is that you actually use this relationship and you don't talk so much about active stress, but you talk about a certain target volume, okay? So active stress is a little bit like reducing volume and you can actually prescribe this reduction in volume. There's an alternative way to introduce active stress. Okay. So we have stress tensor, we have strain tensor, and now we also should have this elastic loss here. And here actually there is a dramatic reduction if I assume that the material is isotropic and linear. So isotropic and linear material. Okay, I also get the details, but it's all written in Landau-Lüschitz. Okay, so if you start from this general tensor of elastic moduli, you can do some symmetry arguments, how many independent components, and I think it is 32. Or is it 41? Just joking. I think it's 32 or something like this, okay? But so this is the largest number of elastic moduli you could have in a completely asymmetric material. But then if you assume that the material is isotropic and of course linear, because we have this linear assumption here, then you actually can show that it cooks down to 2, okay? So you have only 2 elastic constants. So that's why if you are in our fields of matter and biophysics, and I say I have a hydrogel, okay, then you have to specify, let's say, Young's modulus and Poisson ratio, or you have to specify shear modulus and compression modulus. It always has to be 2 numbers. Yeah, and then for hydrogel, it's even easier because we know the Poisson ratio should be close to 1/2, and then we're left with the Young's modulus. That's why all the cell mechanics paper always give you the Young's modulus, right? Because we are usually in an aqueous system, and then only the Young's modulus matters in the end, okay? Also, there's recent work which shows in fractal force microscopy that the Poisson ratio can matter a lot, and it's actually time dependent, but it's more complicated. Okay, so in principle, if you have now only two elastic constants, you can make some simple physics arguments where they come from. It's basically 2 fundamental compression, so it's 2 fundamental deformation modes, compression and shear. So maybe I should write this corresponding to compression and shear. And the result, I write it here, would look like this. So my stress tensor is a linear function of the strain tensor. First of all, there's a term which comes with a elastic moduli which you call lambda times the trace of the strain tensor. So we already clarified that this has something to do with volume changes. Then a Kronecker delta, because of course on the right-hand side you need the IJs, right? General term have 2 times mu, another elastic constant, times I direct proportionality. Oops. Okay, so this is the basis, the material law for linear isotropic elasticity. So these are called the 2 Lamé coefficients. So basically this is related to compression. It's not quite compression, it's a little bit more complicated, but it's related to compression, and this is related to shear. Okay. Now, what about the force balance? So what you now can do is, maybe we have time, right? We started early. So maybe I write this shortly out. What we now do is we take our force balance, which should be 0, and we put in our relationship between stress and strain, right? So first thing I get is, yeah, sorry, I changed the indices here as I have them in my script. This makes it easier for me to check. Otherwise, I had to do it right away. So I'm summing over the second index, but it doesn't matter. It's a metric. I could also sum over the first one, right? It doesn't matter. So let me put in our definition. So the first term goes with the lambda. So this is this term. Then I have the, yeah, so let me write it slowly. So I have this derivative here. Then I have the epsilon kk. So this is the trace here. And I have the Kronecker delta. Okay. And this means that I can immediately replace this by I. Then I have 2 mu times dj epsilon ij. Okay, so next step is to use the relationship between deformation and strain. So here I go to this definition here, right? And I take this definition and replace the epsilons here. And you see it's getting a little bit more complicated because now we get in principle more terms, okay? So yeah, I mean, the first one, we don't have to do much because this is basically this object here. So that's easy. So it's lambda di because we have the Kronecker, it's now di. Then we have dk uk because we trace it. And in this case, these two terms are the same. Okay, so it doesn't multiply the number of terms here. It's only one term. This is still easy. But now the second term is a little bit more complicated. So it's should be actually 2 mu. The derivative. Okay, and then 1/2. So this cancels. That's why it's not on my script. And okay, and then you see that you actually get 2 different combinations. So one combination is that you sum over, let's say this one here, you sum over the derivatives, and this is the Laplace operator. And the other one is where you actually have 2 different indices in the derivatives. And this is like actually taking the nabla of the divergence. So maybe how does this go here? So how do I get to the third one? So maybe I switch to another one here. Now go back to a vector notation. I see that that basically the first term and one of these terms, like this one, are the same. So I get lambda plus mu. And this will be the gradient of the divergence. And the second term will be just mu, but with a 2. No, 1, the 2 is gone. This was the 1/2, okay. And this is the Laplace operator, okay? So this equation here is a really complicated partial differential equation. It replaces our old equation, which was basically something like this, okay? You remember in all our models, we always had the second derivative of u equals 0. And now you see that in 3 dimensions, there are different ways to do second derivatives, okay? I mean, at least we are in an isotropic system, so it should be sort of a invariant contraction of the system, but there's still there are 2 possibilities. There's a Laplace operator, and there's this combination here. And therefore, it's a little bit complicated. Also, you note that while this here is component-wise, okay, this object couples the component to each other, and then you do the derivative. So you cannot solve it in components, but you have to couple them all the time. Okay, so how do you solve this equation? This is typically solved with finite elements. If you do numerics, or you have the analytically, which are in the elasticity books. Yeah. Yeah. So this is a divergence, and then you take the Laplace, the grad. And this gives you a vector. Yeah. So in the end, you have the zero vector. Okay, so one thing which analytically is luckily our first case, okay? So connection to our mechanical tests. So I look at this situation again. And in this case, I can actually calculate, I can find a solution of the deformation which solves this equation here. So first of all, it go like sigma over E. This is obvious. This is what we had before, okay? The larger the stress, the larger deformation, the larger the modulus, the stiffer the material, the less the deformation. And then we will have a number, which I will define in a minute. I call it mu, so it's minus mu times x, minus mu times y. And then I have just a set in the and these two numbers are, of course, the Poisson ratio and the Young's modulus. Okay, and because this is a solution, this E, right? They have to be functions of, and the definitions are, so E equals mu times 3 lambda plus 2 mu divided by lambda plus mu. And the Poisson ratio is lambda divided by 2 lambda plus mu. You see immediately the Poisson ratio is dimensionless because it's the quotient of. They're all in Pascal. Then you can calculate the strain tensor, easy, okay? So what you have to do is, let's say this entry here, it's the derivative for x of this, okay? So minus mu. Then the derivative of this for y and z are both 0. Go away, same thing here. Here, get the same thing. And here you have a 1, derivative of z. And they are also again 0. And then there's the sigma over E in front. So this would be strain tensor. And now you can do the trace of this. So it comes out to be basically sigma over E. And then you sum up here 1 minus 2 times mu. And I told you earlier that this is the volume change. Okay? And now you see something very interesting. So if you take mu equals 1/2, so Poisson ratio 1/2, then, okay, so there will be no volume change. This is the incompressible limit. One can show that the Poisson ratio should be between plus 1/2 and minus 1. Okay, so in principle, it can be negative. So a negative Poisson ratio means that I'm pulling in one direction and things are moving away in the other direction. Okay, rather than the sort of intuitive situation that I'm pulling in one direction and things come in the other direction. Okay, and the famous example, this is the only experiment I can do here, right? Is this. So piece of paper, I crumple it. I love this experiment. You see, I'm pulling in this direction and the material comes out in the other direction. That's negative Poisson ratio material, okay? And the reason is that paper actually crumples. It makes these ridges. And therefore, I basically open up these ridges and they go the other way. Okay? And they create the volume here. It's really cool. And actually, there's an interesting work coming out of my collaborator's place. they're used to positive Poisson ratio material. Okay. So this is the basics of elasticity theory. And what I now want to do to close the system, I want to remind you that we can go back to our viscoelastic model. So also our viscoelastic model can be, yeah, how do I say this? Rewritten in 3D or extended to 3D. Basically had two models. I start with the solid. So this was the viscoelastic solid. And I also put in now active here. What we want to do? We want to look at contractility of cells. So basically, simple, I write F equals FA plus FP, so passive and active parts, because I'm always arguing that the myosin is to all the other stuff in the cell. It's basically connected in parallel. It grows typically on them. And then my old equation was actually that the one-dimensional modulus times epsilon plus the one-dimensional viscosity. This was my passive part. And the active part I usually take to be a constant proportional to the chemical potential difference of ATP hydrolysis. Okay, and what I now can do is I just take these equations and I rewrite them with what I learned in 3 dimensions. Okay, so the way I do it is I write the passive part, so I write the overall stress tensor minus the active stress tensor. So this would be wait a sec. I'm sorry, I'm on the wrong part. So I need actually this equation here, okay? So I write sigma ij minus sigma ija. So I just look here. So is the force. So the passive force is the overall force minus, okay? So I write the overall stress tensor active. This is this term here. And now on the right-hand side, I just have to put this into vector notation, into tensorial notation. So basically the way I can write it, and then we look at it, I write a term which has no derivative, then the time derivative. And down here, I just write the strain tensor, which is here, but I use the form which I gave you, okay? So lambda, the trace, the Kronecker delta plus, is it here? Yeah. That's it. Okay. So this is now the 3-dimensional formulation of the Wind-Voigt model, because here's this is the elastic part. Sorry, this is the viscous part. This is the elastic part, because here you have no, other way around. This is the elastic part, this is the viscous part. So we have basically the two, in this system, we have the two forces. That's why you have one. This is the model. Okay, and then the other model we have would be the active. Yeah, now I would write active fluid if it was only the viscosity. Yeah. Okay, so I would like to write the Maxwell model, okay? So of course, in the Maxwell model, I have okay, this we call a gel from now on. So I would call this the active gel. Okay, and what I do is I just take the equations again. So the force is again active plus passive. And I look at the constitutive law. This was C times epsilon plus C eta epsilon dot. This was the passive force. And now I do the same game again. I convert this into our tensorial notation. So you see that on the, wait a sec. Yeah, this was wrong. Yeah, this because I changed the sequence for my notes. This is not a good idea. Sorry, guys. So again, this is the correct. Yeah, sorry, it's the other way around. Okay, here we have epsilon, epsilon dot. We have only epsilon dot, but we have two forces. And then in the exercise I gave you, you have the standard linear body where you have actually all four terms in one equation. So this was our equation. Now I rewrite it. So let me see. We have now the forces twice. So I write sigma ij dot is this term minus sigma ija. This is the passive part. Dot. Then I have 1 over tau sigma ij minus sigma ija. This is the left-hand side. Right-hand side, I have just the time derivative. And then of the strain and elastic constant. So I have to write again the full expression, lambda, the trace, omega delta, plus 2 times mu, the strain tensor. Yeah.
I mean, of course, I agree with all this.
But
just wanted to say that we don't really have an a priori reason why the active stress can't be time dependent or.
Yes, of course. No, of course.
It's a very special type of
Yeah.
active stress.
I completely agree, Sheila. It's just the equations we used in our work. But in general, this is of course a very special situation. Okay, so the active stress could have its own dynamics and so on. I completely agree. Yeah. Yeah. Sorry. Okay. So now we have equations which you also can put into FEM solvers. And in our group, we always use Phoenix for the for most projects. Sometimes for more complicated projects, we use Dune, which is a very special software. But in principle, this is something you can immediately type into an FEM solver if you want. Okay. So usually for the problems, we look at no way to get analytical solutions. The analytical solutions we can get, I showed you already, these are dimensional systems, okay? But for cells, you often do 2D because the cell is flat on the substrate. There are some simple cases where you can actually solve it with Bessel functions and area functions, but in many cases, you then do some numerics. Yeah, you have to top all of this off, of course, with the force balance. So this has to be supplemented by gradient of sigma equals all the which could come in addition, and this could be adhesion forces, friction forces, things like this. Okay, so at this point, I would actually switch to the slides again. I would switch to the slides. Very good, thanks. So first thing, I have now put 3 PDFs on the Google Drive, in principle for the 3 lectures I gave, okay? And I also did something else. I updated my exercises. So for the closed exercises, I gave a little bit of a hint. And for the open exercises, we clarified a question I got yesterday, and which turned out to be very non-trivial. So I had to actually ask my students to explain it to me. But it's now, I made this comment in the tech file, so you can look at it, why this coordinate transformation works the way it works. Okay? If you're interested in this exercise, it's actually pretty complicated because it turns out that if you write the maximum model, it's not Galilei invariant. There is a thing called a co-rotational derivative, and this explains one of the terms, okay? And then there might be some other terms which you can show do not appear, and so it's not trivial. So thanks for the guys who yesterday actually pointed out to me it's not so trivial, because you have to, in this model, you have to transform integral boundaries and domain sizes and everything at once, okay? So I hope this is now clearer. So as it's written in the paper, it's correct, but you have to understand that there are some arguments to get to this. Okay, so let's talk a little bit about traction force microscopy. And I actually now have introduced some of the concepts we actually use. I'm not going to talk about the details, but the idea is clear. You put a cell, you place it on a substrate which has elastic character, so a Young modulus and a Poisson ratio, and you put in fiducial markers, and these you can track easily with the usual programs like PIV or digital volume correlation, okay, you name it. And then you get the deformation of the substrate. And from this deformation, you actually calculate back to the forces. So this is another cartoon where we don't look from the side, but from top down. Okay, so I see this fried egg morphology of the cell. It has adhesion sites where most of the forces are transmitted through. And we want to actually calculate these forces. And this is actually my first paper in this field. I feel sort of moved if I look at it, okay, long time ago. But we actually managed at that time to measure the forces at single focal adhesions, as these arrows here. And we actually found this typical size of 5 nanonewtons, which corresponds to 5 picopascal if you talk about micron-sized adhesions, okay? So this was the first paper which really gave these numbers. Anyone wants to contradict this statement? But I think so. So I think the traction stresses were measured by Mike Dembo. Yeah, but his method was very coarse-grained, ours was better. And nobody yet had that number for the single focal adhesion, okay? And it's interesting because I told you the typical force which a single molecule can sustain is piconewtons, okay? So you see that you necessarily need thousands of molecules in a focal adhesion, and this is exactly their size. It's like thousands of integrin receptors to make the system stable. And then later we developed more sophisticated methods. For example, we looked at Fourier methods and came up with some new schemes together with Margaret. And you see that now we actually track many more beats in the substrate. We get a very high resolution image, and we can calculate the forces. And you can even go through one of these adhesions and look where the forces are. Okay, are in the middle, are the sides, and things like this. So this is traction force microscopy. And honestly, the resolution of traction force microscopy has not changed so much. Why? Because there's an intrinsic limitation of the elastic substrate. And if you really want to get to a better spatial resolution, it's a good strategy to use these tension gauge sensors, which Mike, for example, is using, and others. So I think it's not a problem, it's just a resolution issue, okay? With an elastic substrate, it's exactly this nature of continuum mechanics. Everything is continuous, okay? So if you know a few deformation, you basically know all of them. And then you cannot go lower in detail. Then for actually quite a while now, we became interested in optogenetic activation of cell contractility. And this is another project with Margaret and Patrick Oakes. And the idea is that you engineer something into the cell, which if you expose it to light, leads to myosin contraction, okay? So there is this interesting pathway in the cell, which is called the Rho pathway, which makes sure that actin and myosin is always synchronized, okay? And this is a high-level control structure in the cell. And if you actually go into this master regulator and you control it, then you can control that you get productive force generation in the cell. Okay, and many groups use this now. And I just show you this movie here. So this is Patrick Oakes shining in these little rectangles here, and he makes them larger and larger, and you see you get more and more forces, and there are some interesting observations. First of all, you don't get forces in the area where you actually shine in the light. For several reasons, but I think mainly because you rupture everything in this region. Okay, these are the highest forces, so to speak. But you get a lot of forces here at the periphery, and the reason is that there are stress fibers running through the system. Okay, so there must be a stress fiber running like this. And then you activate in the middle, and you see it at the endpoints that the force comes to the substrate. Okay, so for this kind of experiment, you now could use all the models I introduced. This was the purpose of my introduction. You see the two models which I just had on the blackboard. So you could do an active solid, you could do an active fluid or gel, if you wish. And it depends a little bit on the context of the experiment. Patrick actually took. Why? Because he was shining in a small part of the cell. Okay. Therefore, it's a little bit like the experiment with Mike explained, okay? He actually destroys the blebistatin. There's an effective contraction in the middle, exactly like the Rho activation, and then everything flows in, okay? So because you have sort of this imbalanced situation where you activate a little region and the rest is like a big pool where stuff is flowing in, we thought that the Maxwell model is a good model, okay? So then we just take a Maxwell chain, we activate in the middle, you get these sort of sawtooths, one activation after the other with increasing power. And then in principle, we can actually extract numbers. You should note immediately, it's a little bit weird that I write Young's modulus here because it's a one-dimensional system. We actually only can get the C, the one-dimensional modulus, and then we have to make some assumption about the cross-sectional area, and then we get the modulus, okay? So we want to give 3D values here. That's why we have to do this little transformation in the end. Yeah. Yeah. Yes, exactly. Yes, exactly. So when I look at this data, I thought we should have used a Kevin Voigt model, but we didn't. But it doesn't make a big difference here. Yes. So actually, this is a very nice data set. And at that time, I think we were not 100% sure if there's really recovery. And then we had this other project, which I'm coming to, and there we saw that the recovery works nicely. Here I'm a little bit unsure because we only shine in a sub part of the cell. Yeah, yeah, exactly. So this trace looks like it recovers, others didn't. Okay, so I think it was okay to use it this way.
So are you shooting all this? Or how many?
Yeah, good question. So first of all, it's a stress fiber. I mean, basically, we activate the stress fiber in the end. And there, I would assume that it's relatively homogeneous, but we can never be sure. Okay. But one problem in these experiments is, I'm sorry if I now have to talk about experiments done by Margaret. But one problem is you have to count the number of fluorophores you use, right? So we are using an elastic substrate with 1 or 2 fluorophores for the beads. Then we definitely want to see something of the cell. So maybe we had Paxilin, I'm not sure. Did we have Paxilin or Vinculin? We had something to see the adhesions. We had Paxilin, right? It's for probably the ref fibroblast shells with Paxilin in them. Or was it U2OS cells? Yeah, okay, the 3T3, right? Yeah, so we probably have something to see the adhesions. And we need, of course, the light-sensitive constructs in it, okay? So at some point, you're limited and you cannot actually extract more information. So it would be, of course, nice to see everything, like what is the size of the sarcomeres. But I mean, for me, it's in this case relatively unproblematic because I think about each of these as one sarcomere. And they have this typical size of 300 nanometer or so. So it's a discrete number and, okay. So this is a coarse-grained version of a sarcomere, if you wish. Yeah. Yeah.
It don't matter that there's, I guess, this now other field that says it's the cortex and these are the 10 folds.
Of course. Would make a difference, yeah. But I mean, we also saw these large forces at the focal adhesion. So for me, it's an evidence. It's mainly the stress fibers. But yeah. Yeah, of course, it's complicated. This is the simple way to analyze it, yeah. But as I said, to make it better, you need more information, okay? So let me come to the, okay. Yeah. This is just a cartoon. I don't know. I had to read the supplement for this. No, actually, no, wait, I have to correct myself. So I think we take the continuum limit anyway. So I think, yeah, what we do is we give a, yeah, maybe this was also leading here with the sarcomeres. I think we take the sarcomere size and send it to 0, and we do the kind of continuum limit I talked about with a density of spring constant and things like this. I think this is the way we did it. And then you can, again, go to Phoenix and actually integrate it as finite element problem. No, I don't think it was a discrete thing. No. Right, long time ago. Now, this is another project where we teamed up with the group of Martial Ballon at Grenoble. And the differences here is that we now actually did whole cell activation, okay? So rather than shining in a little part of the cell, we shine in on the whole cell. And the reason it works here, it's my understanding, we have a different optogenetic construct, which is a little bit weaker, right? So this is, I mean, the one which we used with Margaret is the so-called Love domain. It typically leads to very large forces. These are weaker forces. And then the cells contract, but they don't rip themselves off the substrate, which could be a problem with the other construct. And then what we found is a very nice relaxation behavior. So you basically have cells on different sizes. So these are different micropatterns. Let's take the one in the middle. This is 1,000 per micron. You shine in the light only this little bit here, okay, only for a few very short time. So here, down here, you see that this is, I don't know, 50 seconds or something like this. You shine in the light, and then actually it takes some while, but then the force comes up, and then it goes down again, okay? And here we get perfect relaxation back to the baseline, okay? Because I think it's a closed system, it's a whole cell. Nothing can flow in this sense because everything is balanced. Everything is activated. It's really this idea of the constant stress everywhere in the cell, okay? In a cascade manner. So now we don't talk about stress fibers and things like this. In the paper we do actually, but now I don't talk about it today in this slide. Yeah.
Of the applied was different, like it reached a new.
Yeah, but how should we change the rate? Because we can only shine in light.
Duration.
So I come to the power slide. It comes in a minute, yeah. But I'm not sure if the rate is it's something we can really control. Yeah. I'm not sure if this works in this optogenetic setup. Good question. Yeah, so basically now we see that we go back to baseline. And for us, this means it's an elastic model. And we chose the Kevin Voigt model I showed you, which is still on the blackboard, right? So we chose those to analyze the system. And we can do some calculations. And we can, for example, show, and this is really an analytical calculation with special functions, we can show that the area and the strain in the substrate should scale with the square root, okay? Of course, with 3 points, we can't be sure, but at least the third point is a little bit lower, okay? What I want to point out here is the energy in the substrate, picojoule, right? This is what I introduced in the very last lecture. So I made these simple arguments about 1,000 adhesions and things like this, okay? And I told you that in traction force, we often get this picojoule, and it's exactly what we get here, okay? So this is why I introduced these numbers, and you now see how they play out in these kind of experiments. And this is the power slide. So we basically increase power, and you see saturation behavior. So there is a sort of threshold, like Michael has mentioned, if you wish, okay? If you put in too much activation, it doesn't work anymore. The system is depleted in its ability to generate forces. But what I find actually more important is here that we can excite the system even more, okay? So the cell is sitting on the substrate, and it's by no way at its maximum power. You can really crank it up like a factor of 2 or so, you can make it stronger. Okay, this is what I wanted to show here. And I just flashed briefly, you can look at this on the PDFs. the monolayer stress microscopy. So in the monolayer stress microscopy, you have a whole monolayer of cells on a stripe. And they actually contract together as a big supercell, right? So we can apply our model right away. We do exactly the same analysis. This is actually from Schwarz III paper. And then Xavi actually calculated the stress profile inside the monolayer. And this should remind you of the inverted cosine Koch profile, which we calculated, okay? I think this is exactly what we see here. So this is our model of the cell as a contractile bar on an elastic foundation. The same thing is here in this monolayer, okay? It's just a contractile bar. It's a sort of one-dimensional system because it's this long stripe. And I think our theory works. Yeah. Yeah, but they are slowly migrating. So slowly migrating. So at every time point, you must have a stress profile. Anyway, you're completely right that there are details, okay? And I also have to admit that, of course, they put in a lot of elements in the calculation, which leads exactly to the cosine hyperbolicus, okay? So it's not independent proof. I completely agree. But I think it's nice to rationalize these experiments. Yeah, this is what I showed you before. And by the way, I have to do another correction. So in the lecture last time, I was plotting it like this, but it actually has to be like this. Because at the right-hand side, it has to go to negative values, right? The deformation. So if you want to correct this in your notes, this was wrong on the blackboard. Okay. With this, I would like to switch gears now and come to the last part of my lecture series. And now I would like to talk about cell migration. Okay, but things won't change that much because I will show you that we already have all the elements we need. Okay, and also the mathematics I want to show you is more or less the same. Okay, so it's just that we have to be more dynamic now. It's less about static contraction, it's now about movement. So let me start with this beautiful work. It's one of my favorite papers in the field by the group of Julie Theriot. And they work on this very nice model system, the keratocyte, which is a cell which in nature lives on a flat substrate, namely on the surface of your eyes. And this makes it such a nice model system for us. Okay, it's a cell which is basically very flat and it is geared towards fast migration because it has to survey the eye for damage. Therefore, it's a beautiful model system for cell migration, for fast cell migration. Now, what they do is they actually do speckle fluorescence microscopy. You have seen this in Mike's talk. So if you actually put a fluorescent label on every molecule of interest, you see nothing, right? Because everything lights up. So what you do is you label only like every 1,000th molecule or so. And then you get these speckles in the cell, and they will move as the actin is flowing. So you can track the flow of the actin exactly in the same manner we track the flow of the fiducial markers in elastic substrates. They track the movement of actin in a migrating cell. And then you actually do this in the cell frame. So you sit yourself in the cell and you draw all these vectors. So you see that there's a very fast velocity from the edge towards the middle of the cell, and it's basically damping down, okay? You also have a flow from the sides in, which leads to a sort of a force dipole, which might even push the cell a little bit more forward, okay? Because it squeezes out the middle. What you see here is that they use 3 different adhesion strengths. So low adhesion means that the cell can't move well because it's basically stuck to the substrate. And then it actually tries to move its interior like crazy, okay? So you get a very high flow, but it's an unproductive flow. It doesn't lead to migration because the substrate is too sticky. And then you go to the intermediate adhesion strengths where you have a sort of modest flow, which means that the other part of the force generation is already used for migration. And then you have the sorry, this was low. Okay, and this is high, okay? I have to be a little bit careful what I'm saying. So in high adhesion, you are stuck to the substrate. In low adhesion, the problem is you cannot transmit the force to the substrate. So both limits are bad, okay? Either you're stuck or you're basically slippery, but only in between it works. So the middle column is the good column. This is where you get productive cell migration. And here you can't migrate very well. But the difference is here the retrograde flow is fast, and here it's slow because it's also stuck. Sorry, I got it wrong. Okay, and then they give actually blebistatin to the system. This is what Mike explained in his talk. And I also mentioned this at the very beginning when I talked about the cross-bridge cycle. If you give blebistatin to the system, you basically prevent the cell from going through the power stroke in the myosin cycle, okay? And then you don't generate forces. And you see that if you put a lot of blebistatin, the flow really goes down in all three cases. Okay, which shows that the flow is at least partially driven by myosin contractility, which pushes it to the back. Okay. Of course, there's always polymerization in the front. This is the other large component. And if you go the other direction, you can give a compound which is called caleucolin. You actually make the myosin to cycle like crazy, and then the flow becomes even faster, and you see that also cell shapes changes a lot. So recently, a few groups have actually combined cell migration with optogenetics. So this is again work by Marcel Ballon, who showed that if you have a cell on a line, okay, and you actually shine line at the back of the cell, it contracts, thereby it ruptures itself off the substrate, and then it starts moving forward. So this way you can actually trigger cell migration. There's another work by Julie Theriault, who actually used another optogenetic construct, not a row, but something different, something from chemotaxis, to show that you can reverse cell migration. So you have a migrating cell, and you basically shine in such a manner that the front becomes contractile and the back becomes sort of more protrusive, and then the cell reverts and goes in the other direction. Okay, so this is basically, there's different ways how you can do it. So this is like the anti-row experiment, okay? So you make this less contractile. Usually it's contractile in the back, but with the CDC 42 activity, you go the other way. So you make this less contractile, and then the back becomes contractile and the cell moves in the other direction. So in principle, you can use optogenetics to reverse cell migration. And then we actually asked, how can we use our simple models of cells to actually predict these effects of optogenetics? For example, can we say how large the area is which you have to activate, okay, the signal strength, is there a certain time of the process where it's best to shine in light, things like this, okay? And therefore we came up with models for cell migration, and this will be the last thing I'm going to deal with on the blackboard. So now I need the blackboard. Okay. Okay. So last part is simple models for cell migration. And I think historically, one of the first papers was by Doug Laufenburger, and they used a chain of Kelvin Voigt models. But we prefer to actually go to active shell theory because it's, yeah, I would say for theoretical physicists, it's more attractive, and it reflects better the constant movement in the cell, okay? While the Laufenburger model, the first paper was a discrete model which had a lot of things actually put into the system to make it migratory, and we look more at the minimal ingredients. So we actually like to do this with active shell theory. So I don't want to say too much about active shell theory. There are actually other experts on the room, but the version of active shell theory I'm using here is really the most basic version. So the standard version of active shell theory has some polarization field in it, and this we don't do, okay? So we don't look at the orientation of the actin, we only look at the flow of the actin. But for our purpose, because here we do a one-dimensional model, that's just fine. Active shell theory goes back to a group of people. So it's basically Jacques Pro, Frank Gülicher, Jean-François Chouany, and Carsten Kruse. And I decided that I start by showing you the Kruse model. So this was, I think, the second paper on active gel theory. So the first paper was something on structure formation, asters and vortices in active gels. And then I think this was already the second paper in physical biology, 2006, where they looked at cell migration. So they basically applied this new formalism to a migrating cell. And you will see immediately why this is a very appropriate choice for us, because it's exactly the same ideas which we had before, okay? Just that it's not a contractile bar, but a migrating cell. But otherwise, the analysis is very similar. Okay, so we take a substrate and we put the cell on it, and we give the cell a certain height. Why is this? Well, the problem is that we basically want to make the force balance, like in this free body diagram we had before. And therefore, this is this free body diagram down here. So we want to make an analysis similar to this one, okay? So that's why we want to really keep all four sides for the moment being, but of course we integrate out the C direction in a minute. Then we now look at a situation where the whole cell moves with a velocity v to the right. And we also assume that the length is fixed, okay? So it has a length L, and this is now fixed. But in the open problem which you have, you will look at a model where this is a time-dependent quantity. Well, I will say more about L later, okay? It's not really fixed, but it will be fixed by the theory later. Okay, what else do we need? We basically have now two elements, okay? So first of all, we have the retrograde flow. These are all the vector fields you saw in Julie Thierry's work. And we can now make different assumptions on where this retrograde flow comes from, okay? And in the work of Carsten, they made the assumption that it's mainly driven by actin polymerization. And later we will introduce two speeds, the speed of polymerization at the front and the speed of depolymerization at the back, okay? So this is actin depolymerization or polymerization. So it's VP at the front, and it's VD at the end, at the back. But we will use this only later. Right now we don't need it, okay? But I already plotted here that you understand that this will be an important aspect. And then it's clear, in this way you force the system to migrate, okay? Because you force it to push forward the front and to retract the back, okay? And what is missing here is the myosin, okay? It's a purely polymerization-driven model. But the problem I gave you is actually a contractility-driven model, okay? Thanks a lot. Okay, so now we do the force balance. So we introduce again this little slab here. And this is our one coordinate, the x. And now we actually just go over these four phases and write down the different forces, okay? So first of all, we have a force which is applied at the left-hand side. So just like this little diagram. So first we take the force on the left-hand side. This will be sigma xx. And we integrate it over the size of the patch. So we go up in z direction from 0 to h. And I write a minus sign here because by definition, the sigma xx goes to the back, but we have to do the force balance on one axis in one direction. So this is a negative force. Okay, then I have the same force on the other side. So this is this force here. And you already see what's going to happen. We will do a Taylor expansion here. Okay. And then we have the two forces on top and bottom. So first of all, I look at sigma xz. So z is now the normal in this direction. So I look here, and I first take the one at the bottom. And this is a shear force, which basically goes in this direction. So I give it a... Now I have to integrate in this direction here. And that's this term. And then the last term would be a similar term on the upper side. So let me write x, x plus dx, x dash sigma x. So it's basically the same thing again at the height h. And these four forces have to add up to 0. Okay, so the first thing we do is actually we cross out that term, because at the upper side, we have a free boundary. So there should be no stress on the upper side of the cell. Then the next thing we discuss this force. So this is basically the interaction of the cell with the substrate. And here we just assume it's a simple frictional force. So we basically... Yeah, that's it. And then we actually integrate these guys here. They are all over small lengths. So this is a small h. This is a small delta x. So we basically can take the, how do you say this in English? Mean value theorem, right? So you approximate the integral by the value of the integrand somewhere in the middle. And so we now define sort of a new stress, which is the height averaged stress. Sorry, this is over, yeah, that's correct. Okay, this is the height average stress. And then the first term would be just the height with a minus sign times sigma at x. This is this integral, then this would be sigma at x plus dx. From here, we get the averaged velocity at position x times the thickness dx. And this should be 0. Now you see you can divide by the delta x. This here gives you a differential coefficient. That's like doing a Taylor expansion. So we basically get that the derivative of the stress should be the friction coefficient divided by the height times the velocity. I mean, in principle, we could have written this right away because we already had all these equations before, okay? But I like the derivation by Carsten, and it's also interesting to see this h here because it shows you that it depends a little bit in which dimension you argue. Okay, so this friction coefficient have different dimensions depending on where you define them. Okay. Okay. So now we continue exactly as before. So I write that I have an active system with a passive and an active stress. For the passive stress, I take now just the viscous law, not even a Maxwell. I just write eta times epsilon dot. So I just follow the paper by Carsten. And then you see that the time derivative of epsilon, okay? So epsilon is basically the xv, sorry, epsilon is dxu, okay? And then you do a time derivative of this, then you put it here, and this becomes a v, okay? So that's why this is then dxv. Yeah, the active stress, I just call it P, and I assume that it's a constant. And then you actually can put the things together. So you actually take this equation and do another derivative. Then on the left-hand side, you get the second derivative for x. On the right-hand side, you get the xv. But this is exactly what you have here, okay? So you actually get an equation which brings together the second and no derivative. And what we get would be an equation like this. Okay, and then of course I also replace, so I replace sigma p by sigma, like before. This is the same trick I used over there, okay? And then we have a new length scale squared times the second derivative of sigma minus sigma equals minus p. Okay, in the new lambda here, very similar to also what Julia showed, would be the root of an, in our case, viscosity over friction coefficient, okay? So often you don't see this h, but then you define these two in a different dimension, so to speak. Okay, here it's with the h. So this is the hydrodynamic length scale. So from the interplay of friction and viscosity, you get a length scale. And this length scale is extremely important in biological systems. And depends a little bit on the system you're looking at, but a few tenths of micrometer would be a typical value. Yeah, it's exactly the same equation. So that's why I'm doing it, right? So I show you that we get the same equation again. Yeah, so as Sheila observed, we already solved this. So the solution should be exponentials. So we have divided by lambda plus b to the x to the, and then plus p, because if you plug this into our equation, we assume p equals constant. Here it goes away, okay? Here you get the same thing back, so it's sigma minus sigma, but what is left is the p, and this is what we need. So this would be the solution. And we now have to worry about the boundary conditions. And here again, the usual thing, the boundary conditions. And then you have to have two conditions for the A's and B's. And the solution will be P times 1 minus the cosh. Yeah, but it's a little bit different in the notation now. We go actually from 0 to L, not from, what I showed you for the contractile bar, we used minus L to L or something like this. Now we say the cell goes from 0 to L. So it will be 2x minus L divided by lambda. So as I vary x from 0, sorry, I basically take the symmetric part of the cosh. And down here, I have L divided by 2 lambda. So if you plot the sigma as a function of x from 0 to L, you get exactly this parabolic.
Sharpie's experiment.
Yeah.
This model to me seems more reasonable.
I completely agree that both models give it this, yeah. But the point is his calculation was the elastic one. Just say his own calculation was the elastic calculation. No, yes and no. In the monolayer stress microscopy, you actually make the assumption it's an elastic material.
Yeah. Okay, the 2D stress.
Yeah. But yeah, I mean, there's this work by the French group which showed that actually the Young's modulus doesn't matter, it drops out. And they, yeah,
2009.
yeah, yeah.
Was a model independent,
Okay,
just integrating the traction.
okay, this I didn't know. Okay, I saw this, I was MSM. Yeah, but anyway, the offshot is in principle both the moving model and the contractile stationary model give you this parabolic stress profile, okay? Because the mathematical structure is the same. And then we look at the velocity. So the velocity is just this cosh. Sorry, where are we? No, this is the derivative of the cosh, so it gives you the synch. So this goes from 0 to L, the velocity, and it will look like this. Okay. This is where I said last time I plotted it the wrong way for displacement. I plotted it like this, but it also should have been like this. So you see that you have an extremely symmetric situation. It's basically sitting in the left frame. No, not like we're sitting in the frame of the cell. Everything is symmetric. Okay. So you have what you have now is basically you have a minus V at the front and you have a plus V at the back. Okay. And they're exactly the same. Okay. So the velocity in front and back is exactly the same. And such a system would not move. Okay. But now the trick is that you just force it to move. I think there's two velocities at the sides, right? So what we now do is you basically transform to the left frame. You don't need to transform any differential operator or something like this, like in our open exercise, but it is some velocity. So we assume some velocity, cell velocity V. And then everything should, okay. So in particular, the velocity at the right-hand side, which is the velocity at the right, plus the additional velocity from the polymerization, this should add up to V. And the same thing on the left. So on the left, you have Vd, then the velocity at the left should also add up to V. Okay? So the trick here is, we still have one open, you see, we basically introduced two more parameters, which we have to balance with only one other parameter. This can't work, right? But there's a trick here. We have still the length of the cell, which we can adjust. Okay, so if you adjust the length of the cell, because the length is here, so the lambda is a constant, but the length is here, and we haven't split it by actually a certain value to the length of the cell, you can make this profile coming down quicker or less quick or something like this. Okay, so degree of freedom here in the system. So with this, you can make it. So the first thing is, you know that if you add up these two equations, the velocities at the sides drop out because they're exactly opposite of each other. So the velocity at the right is minus the velocity at the left. Because this model in the cell frame is exactly symmetric. So this will actually cancel out if you split up. So the velocity of the cell would be 1/2 of the two polymerization velocities. It's work. You now also have to fix the length, okay? So after some algebra, you find that the length should be 2 times lambda arc tangent. Yeah, I just write this for completeness. Something like this. This means that we cannot specify the length independently, but if we let it adjust to a certain value, then we can actually match the two requirements of the two velocities. And now we have a cell which is migrating with a certain velocity. Basically has now broken this symmetry, okay? So basically this becomes a little bit faster, this becomes a little bit slower. So the new cell, okay, the new cell now has a faster velocity at the right and a smaller velocity at the left. That leads to an overall velocity v, okay? This is how you can make this model motile.
Why do you have to
Well, I didn't make any reference to absolute coordinates. I just have derivatives, and I basically write the stress from 0 to L, so through the cell. There's nothing which singles out the substrate. But in the moment I go to this velocity here, this is seen from the substrate. Yeah. And it's a little bit like I showed you the slides of Julie Theriault. You can look at the retrograde flow in the frame of the cell and in the cell of the substrate. And what she's doing, she just looks at the centroid. She gets the overall velocity and she subtracts it from the field. And then you get these two different views. And then you see the asymmetry in the system. So it's very close to what she was doing. Okay, so I'm very good in time this time. So basically, what I want to spend the last minutes on is I just briefly say something on our model, which is in the open problem. So up to now, driven that if you give plebiscite into the system, the retrograde flow goes. Polymerization is only one part of the equation, and the other part is the contractility. Okay, so alternative to this, alternative to polymerization-driven migration, we could now write down models for contractility-driven migration. And like always, the truth is in the middle, okay? So cells have one part polymerization, one part myosin conductivity. I think the two things go nicely hand in hand, okay? It's like always, this is a complex system with many aspects. So using the myosin for increasing the retrograde flow lets the system coupled better to the rest of the cell, okay? Like mechanosensitivity, for example. If you only had polymerization, the lamellar podium is a rapidly branching actin gel, it would not be coupled so well. Okay, this is one explanation why it's good to actually have this conductivity in there. So you can now ask the question, can we write down a model that is only based on conductivity and still get migration? Okay, and this is the question which has been asked by Pierre Ricot. So I call it the Ricot paper. This was a PRL. And he had a system of differential equations. So differential equations. So PDEs basically both for the sigma and for myosin concentration. And if you write down this equation, you actually find something which is very similar to a very famous model in mathematical biology, which is called the Lee-Siegel model, and which Eduard will talk about later anyway, okay? So it's a very important mathematical structure. So what fact that you have to fix the L here, or that the L is fixed by the model. So he introduced a boundary condition for L, which I call the elastic boundary condition. So basically the idea is that this is the migrating cell, Now the retrograde flow is driven by some myosin concentration, which typically looks like this. So the myosin concentration, how do they call it? Yeah, myosin. Basically, you have more myosin in the back, so you pull the system to the back, okay? And then he introduced a boundary condition which you could draw like this. That he basically has this L to be a dynamical quantity L of t, however, which is constrained to a certain reference value. So the cell wants to have a certain size, which I can fix from the outside, okay? And this makes a lot of sense because we know that volume control in cells is not so much related to these processes, okay? And it's weird if you need the active shell model to fix the volume of the cell should be fixed. So I think this is a very, very reasonable assumption here. So yeah, so Pierre's model is pretty complicated, and therefore we actually came up with a model. So this is the Trodowski paper. So this is a little bit difficult here. So our paper, which I gave as an open problem, is work by a great graduate student, Oliver Trodowski, in PRE. 21 was the first paper, and we now have 2 more papers. But this is the one we gave for the open problem. And I just write down the equation that you see how it looks like. So what we use is a Maxwell model, which means we also have an elastic aspect in the system, not only viscous, like in the model by Carsten. And we have no concentration for myosin. Okay. Then it will turn out that there is no motile solution, because, I mean, Pierre showed that you need the concentration field to get the motile solution, but we replaced the concentration field by optogenetics. Okay. So by putting in optogenetics, you can also create gradients. They're not self-organized, but you can put them in from the outside, and then the model becomes actually motile again. And then in the other paper, so in the later paper, we showed that if you take the full model of RECO, we can do both optogenetics and self-organization of the myosin. Okay, so just to flash to you how the equation looks like, it's basically a Maxwell model. So you have something like this. So this is the viscous part, this is the elastic part. And then we have a strange part, which actually is a so-called co-rotational derivative. So it's like in the Navier-Stokes equation, if you wish, okay, you have a moving system and you have to do the right transformation. So this gives you another term, which actually turns out to be not so important, but I mean, in general, it's good to have it. Then this is the passive part of the system model. So you write overall stress minus active stress. This is the passive stress, and you get with some friction coefficient. What is this? Okay. Now here you actually, okay, this is still the Maxwell model. So this is the viscosity times the time derivative of eta of the strain. And again, the same argument as I explained before. This is then the position derivative of the velocity. Okay, and then you complement this by the usual force balance. So the divergence of the stress should be the friction times the velocity. And if you put this together, you get an equation which looks very similar to the other equation. Okay. This is the fact that the Maxwell model is not Galilei invariant, and you have to do this co-rotational derivative. Yeah. Actually, I didn't know. I was asked yesterday, and then I realized that Oliver put it into the model. Yeah. I sort of didn't know that. Right. Okay, so this is basically the model. So we put it together. We have to write this again. You basically get a time derivative. Now you get actually, okay, no. You get tau divided by the friction coefficient, dx sigma, and then another dx. And then you get on the right-hand side sigma minus sigma A. And this is new length scale squared dx squared sigma. This is the equation, okay? So this is our central equation. We look at the paper, and you see that it has some elements of the other equation, but it's even more complicated now because it has a nonlinear part here. So it's quadratic in sigma here. And yeah, otherwise it looks very similar to what we had in the other models, right? So the offshot here is that you always end up with very similar structures. And as I said, Eduard will talk about the Siegel model anyway. Okay, this is where I want to stop. Let me try to summarize. So I actually started with traction force, and that we want simple models for contractile cells. And there we use this contractile bar, okay? Then I showed you if you have a real cell spreading on a substrate, we need at least 2 dimensions. And therefore we have to write everything with tensors and vectors. And this will typically solve finite elements. And then we switched over to cell migration. And I showed you that you can use this version of active shell theory to write down models for micro, but you put in polymerization by hand. And therefore, we finally went to a model where we have also contractility in it, okay? And I showed you some of the simplest version of this, which is already complicated. And the more elaborate version actually is our communication physics paper. There would be even more terms, a new field, more terms, and more coupling, okay? And then you have to do a lot of finite element or finite volume modeling for this. But it's really fun to work with these differential equations. They are very well understood in mathematics. You can do bifurcation analysis. You can develop rigorous criterion when you get migration and not. So we would say that the minimal ingredient is either some polymerization at the boundary, which is, however, not really part of the model. You put it in by hand, or you have spontaneous symmetry break in the system that the concentration field of myosin arranges such that you get migration. But you could also use optogenetics to replace basically this requirement. No. The sigma is a function of x and t. Yeah, sigma is constant. Yeah. Yeah, of course, you could now come up with more dynamic versions of sigma A. Completely agreed. But usually you say sigma A is an activity coefficient times the chemical potential difference. How you get it? You don't get it in this model. No. This model will always relax to a non-motile state. If you turn on the optogenetics, make it run for a while, but if you turn it off, it will become sessile again. And you need a second field to get the symmetry break. Would also do it, yeah. Yeah. So I think in our first discussion on what we should pose as the exercise, we actually had a gradient in sigma, which is given, and then it also migrates. Very good. Okay, then any questions? No, then I think I thank you a lot. Or there's one.
In one case, there's a gradient in stress.
Yeah.
In another case, there is more like the polymerization.
Yeah.
Can you maybe talk a bit about with systems which model would be relevant or both are relevant at this time?
Yeah, I think it's so the question was when is the contractility more important and when is the polymerization more important? I think it's really a matter of cell type. This is exactly what basically genetics can play with, okay? So, and signals from the environment. And I would say in the keratocytes, of course, there's a lot of polymerization, but maybe in a fibroblast, it's more contractility. I would say those cells which have large traction forces, they probably have also a lot of internal stress. And then we would be more in this contractility-based model, okay? And then there are other models like the keratocyte, or the white blood cells, which just polymerize very quickly, and which actually, tend to be also the ones which are more chemotactic, because you see, if you get chemotactic signals from the front, you can easily activate WASP and UP2/3, and then you just go, okay? While the contractility thing is much more complicated. I mean, you have to basically do raw activation, and if you have a lot of these front signals, you actually downregulate raw, okay, because you now focus on polymerization. So I think the answer is that the contractility-based motility is more important if you have slow cells, which want to mechanosense more. So we know, for example, that fast-moving cells typically do not mechanosense so much as the slow-moving cells. So I would say, actually, it's a very good question. I start thinking about it. I would say it's a trade-off. If you want to move fast and you have to catch a pathogen or you have to get to the next lymph node, maybe you don't care so much about mechanosensing. And this is what Michael 6 actually showed, that the lymphocytes typically, or neutrophils typically don't mechanosense so much, okay? But if you are a slow cell, maybe you are fibroblast in connective tissue, you have to repair tissue or something like this, then you don't have to move so quickly, but you have to know exactly what the mechanics is like. And then you're probably on the other side. And then I think this is what the synergy I talked about, okay? So if you use contractility for mechanosensing, why not use it also for migration? That the same system is already turned on. Yeah.
Cells like MDCK, fibroblasts, would you say exploring more on that side?
Well, MDCK cells are really epithelial cells, and they are meant for monolayers. So I mean, of course, they are migratory if you let them sit around alone, but in principle, they're really epithelial cells. So they typically don't have so much integrins, more cadherents, and so on. I wouldn't now look at them as primarily motile cells, okay? I would rather compare the neutrophils, which are very fast migrating cells in our body, which have to get everywhere very quickly, with fibroblasts, which you need for wound healing. Okay, these are my more favorite model systems. Okay. Yeah, right. Yeah. So, excellent question. Our paper on this came out yesterday. It's a new journal of physics. I already put it into the PowerPoint. So it's not a paper on focal adhesions, but it's a paper on gradients in adhesion. Okay, which is the first step towards focal adhesions. Yeah, so we looked at this. Yeah, exactly. So the offshot is that if you have a gradient in adhesivity, of course, you also can get these guys to come motile. Yeah.
This kind of asymmetry and complication can explain why cell migration on the stiffer substrate can migrate faster.
Okay. Yes and no. So first thing is that if I think about our models, we always have this layer of springs, and there's no reason not to put their gradient. Okay, you can put a gradient in spring constant density, so you can look at sort of stiffness gradients in the model too. But I mean, what we don't really have is a feedback which actually increases the feed stiffness as a function of stiffness. What is mechanosensing typically doing? So then we would need to do a new model, which is more complicated. Yeah. So I mean, I want to say this is continuum mechanics. Okay. There are specifically no focal adhesions in it. Okay. But if you're a little bit used to the arguments, you can argue about focal adhesions, but it's a little bit far-fetched because they're not really modeled here. Yeah. But you can have gradients in adhesiveness, gradients in stiffness, that's all possible. Yeah. Yeah. So I think it's an interesting viewpoint that you have gradients inside the cell, like a gradient in myosin concentration, you have a gradient outside, and then you can ask how do these two things communicate with each other. Yeah. Okay, time for lunch.